Hi everyone, we're going to do a quick intro on what 3D printing is. It's a more modern technology, but a lot more people have heard of it now than they have even 10 years ago. I'm sure most of you, if not all of you, have actually heard of it, may have actually seen it, and may have actually 3D printed themselves. Basically, what is it? 3D printing is an additive manufacturing process. What that means is that it's continually adding material versus a standard machining process where you start with a block of material and you're taking material away. Usually it builds with polymer, so like plastics, resins, things like that. But more recently, metal has become a lot more popular. There's more affordable machines that can do it. When metal sort of first came out, the machines themselves were $1 million just to do it. Now they're down in the $100,000 price range, which is still pretty expensive, but definitely something reasonable for a company or even a school to have. It typically builds layer by layer. What it's doing is it has a vat of resin here, and it's taking a laser, and the resin cures with the laser, and it's doing basically one row at a time, or one level at a time, and then it just keeps moving up. It's great for fast turnaround of parts, so sometimes you get a lead time from a machine shop of a few weeks. You can typically 3D print something in a day. All the little pieces you have. If you're wondering about your kit itself, the total amount of hours to print one kit of parts was about 8 to 10 hours. So that's including all the little pieces for your flute, the mouthpiece, the ukulele, bridge, and the bell. But 8 hours to get, a completed project is not too bad. And then one thing we'll go over is that different technologies get you kind of different characteristics. So the primary one, actually the only one that you guys see in your kit, is fused deposition modeling. This is where it's taking normal thermoplastic. So this is the same type of plastic you'd see anything if you have like a phone case, your computer mouse, your keyboard. I'm just looking around my desk, and half the stuff is made out of, typical engineering thermoplastic. Basically, a thermoplastic is any type of plastic that you can then melt down and reform. Then you have photopolymerization. That's the one that I kind of described in the previous area, where you have a liquid resin, so it starts off as liquid, and it takes some sort of light source to then cure it, to make it harden. So in the most of these use UV light. There's a lot of UV sensitive polymers. You can selectively pick where you're going to cure the resin. Then you have selective laser sintering. This was one of the early popular ones. So it takes you have a big bed of powder, and then you do the same thing with the laser. So instead of using a light to cure the polymer, you're taking very, very small, it's basically like plastic dust, where you're taking a laser and you're fusing it either with heat, or there's sometimes a binder that's in there to hold everything together. And it just does one layer at a time, just doing the same thing similar to SLA. And then you have direct metal laser sintering. This is the newer one. This is again where you're doing, it's usually a powdered based metal. Sometimes it's bound together in a filament, kind of the way FDM is, and sometimes it's just completely powder, kind of like the SLS. So fused deposition modeling, this is the one that most people are familiar with. These are your MakerBots, your Ultimakers, your Prusa, whatever. These are, if you've been to the Science Center, this is in Cabot Library. This is what you see up on the wall there. It's what we have a lot of in our labs, in the active learning labs. It's pretty easy to use, and it gets you your normal thermoplastic that you want. So it builds parts. Again, it's a continuous strand of material, so think of it kind of like a hot glue gun, where you heat something up, you squeeze it, and you get this strand of plastic out of it, and then it just kind of goes in a pattern and does it layer by layer. Again, this is what we used to make your parts, and your parts are all made out of ABS. That's the type of plastic that's used. You can print. One of the benefits is you can print semi-hollow parts. You don't need to have a solid block of material. Your parts I actually printed solid because I didn't want any air to leak through them, but you can make lighter parts, especially if you're just prototyping. If you just need the form of something, you don't need it to be solid plastic. The tolerances are okay. If you don't know anything about tolerances, these probably don't mean anything to you, but you can get in pretty much close to tolerance of the size of a hair. So 3/1000ths, I think between 3 and 5/1000ths, I think, is the size of a human hair. So you can get accuracy to that point. The Z resolution is going to be coarser, so if you notice, if you look at your parts, you can kind of actually see all the layers. That one is more restricted on the nozzle size of the printer, so you might have less accuracy there. And then minimum resolve features you can make fairly small, but not, it depends on your definition of small. It's great for big projects, and big again is relative. The print bed of our printers, the largest one we have is 14 inches by 12 inches by 12 inches. So you can print anything in that. If you filled up the entire bed, if you filled up that entire volume, that would take a few days to print. So before we move on to next, there's support material and post-processing. This is something that all printers need to some extent. So because I said we're sort of heating up a thermoplastic, kind of squeezing it out like a hot glue gun, before that solidifies, it's going to be droopy. I usually like to compare it to like a spaghetti noodle. Think of like trying to hold a piece of spaghetti when it's dry is fine. You can hold it on one end, but after you cook it or when it's wet, it doesn't really support itself. If you hold it sideways, it's just going to drop. So you need something to support that up until it dries again, or until it cools in this case. You can either use the material itself and you just break these apart. It kind of leaves marks, and you have to do a little bit more sanding and filing and stuff. Or what you can do, and it's hard to see here, but they probably did actually do some sanding here. Or you can see this picture here where there was soluble support. So this is the brown material here. This is all stuff that dissolves away after you print. So when you're done, you don't have any marks whatsoever, and you can do much more detailed, you can do much more intricate parts that way, so that you get all the features you want without having to design specifically for 3D printing. Stereolithography, so this is SLA. This is the one that there was the little animated GIF at the beginning for. So it's a resin. So by resin, I mean it's something that cross-links, which means, I guess the easy way to describe is it hardens when it's exposed to either chemical. So if you have ever used two-part epoxy, that's kind of what's going on there. But in this case, it cross-links with UV light, which means it hardens when the UV hits it. Because it starts off as a liquid, you can get very, very fine detail in these. So you can see that the tolerances are much, much tighter. So this is much less than a human hair. So the other one was, I think, 3 to 7 thousandths. This one is 1/1000th of an inch, or 0.03 millimeters. Again, sorry for those that like metric. It can also do a lot smaller because it can do better resolution. It can do much smaller features. This is great for small parts. It's not awesome for anything that needs to be structurally sound. A lot of times with SLA parts, if you don't treat them with a UV blocker, or if you don't take care of them well, they'll continue to sort of cross-link, and they'll start to become brittle over time. But again, you're going to think of your application before you think of what you're doing. Time, speed-wise, comparably, they're not too much difference between FDM and SLA. Sometimes one is faster than the other. These will print solid. If you want them to be semi-hollow, you have to do that yourself in CAD. It won't automatically do it in the software for the 3D printer. And then, likewise, it needs something to support it. The liquid itself is not structurally sound enough to actually support the material as it's printing. So it does these sort of scaffolding that you break off. You get tiny little bumps where they are, but you can usually sand them right off. Usually don't want them on any internal features where you can't get to, or any features where you don't want to sand it. And then the post-processing time isn't so bad when it comes to removing the support material. You just break it off and sand it. It doesn't have to sit in the bath for like a few hours. Why you would use 3D printing, when it's useful. So think about what you're trying to do. In your case, I 3D printed a lot of the flute parts just because it would have been a lot easier for me to do the 3D printing than if I had machined all those. Each of those pieces, well, the mouthpiece couldn't. So the mouthpiece is kind of considered a complex part. If you look at a typical recorder mouthpiece, which I kind of base this a little bit off of, they actually are made out of 2 or 3 pieces, if you look at them. Because you have that little pocket inside where it's kind of considered trap material. If you were to try to machine it, you wouldn't actually be able to get those different diameters. And then you have some other complex parts to it where if the whole inner diameter was the same size, you could probably machine it, but the way it's designed, you can't. Very small parts are really hard to machine unless you have specialty machines that are meant for machining really small things. Testing fit, so if you just want to test things out, say you were going to make something out of like aluminum or steel, but you wanted to make sure everything fit together before you spent all the money to go and get it manufactured. It's a great test for that. Prototyping molded pieces, I put this in because FDM is the same exact plastic that you would use in injection molding, so you could test it out there first. It is going to be weaker though than in injection molded pieces, just basically because it's building layer by layer. You're not getting great bonds between the layers, versus an injection molded piece is a solid piece of plastic. Any cosmetic parts, if you don't need them to function, a lot of times industrial designers will send prototypes. They'll do what's called a looks like prototype, where it's just something that looks exactly like what you're going to make, but it has no function in it whatsoever. It's sometimes 3D printed and then sanded and painted. And then one-off parts, like if you only needed one of something. When not to print, so when another manufacturing process is faster, I actually debated getting the smaller flute pieces injection molded, but the lead time was okay, but it was going to cost thousands of dollars just to get that done to you. So cost might be another factor. It's not listed here, but it's one of those things where you have to balance sort of your cost and your time you have. If you need very specific material properties, like I said, you can't completely replace injection molding with 3D printing. You do lose some strength in the parts. Same thing with metals. If you have some sort of exotic metal, obviously you can't 3D print it. And then basically you should also not print if you can just easily make it out of some other material. So if you could just make something out of cardboard just to get your point across, you wouldn't want to use it there. And then designing for 3D printing. So this is kind of why we went over a lot of CAD. The CAD is just to get you started so that you know how a typical engineer would start with creating a product. Sometimes you do just start in cardboard or foam core and you cut things up and you kind of glue it together, and it's kind of like an arts and crafts project. It's pretty fun. But then you need a digital file in order to 3D print. So if you know you're only going to be 3D printing the part, there's some design considerations to use, but if you know you're going to use a different manufacturing process afterwards, you might choose some different design considerations. And then just knowing ahead of time what type of 3D printer you're going to use is useful. So you got to know how big your part is. You need to know what the function of your part is going to be, and you need to know how much detail you need, because they're all going to cost differently, and they're going to take different amount of times. And just considerations. You guys probably won't be designing anything for 3D printing in this class just because we don't know how to get the parts to you if we do get them. But for future class, if this is something that interests you, once the world is back to sort of normal, we'll have a makerspace over in our new campus building in Alston, so in the new engineering complex, and you guys should be able to just come over if you want, 3D print. Some of you might live in houses that have 3D printers, so it's just useful to know some of these tips and tricks in case it is something that interests you. These are looking at it for two different views. Say you had, this looks kind of like the flute piece. The flute piece was printed perpendicular to this, so it's more like this, where each of the round layers was printed flat, versus if we rotated the piece sideways, kind of like if we rotated it like this, your circles wouldn't be very round. You can kind of see this a little bit on the pieces of your flute that have the holes in them, the side holes where like the finger holes would be. You can see that it's not a perfect circle, and you can kind of see the ridges, so you can kind of see how the layers work. You can also look at different ways that you orient. So when you go to 3D print something, you have to load it into this separate software that does what is called slicing, and slicing is what it does to create these different layers. So this is just a simple part. It's a completely arbitrary part, not for anything, but just to show some concepts. If you were going to print it sideways like this, you can look at both the time, the material, and how much support material it's going to use. Versus if we printed it vertically, right? It doesn't have to support anything in there. So it's going to take much less time. It's going to use, a tiny bit less material. I'm not exactly sure why. Probably has something to do with the wall thickness when it rotates, and then definitely a lot less support material. It's also going to be, again, this circle is going to be much rounder. It's not going to have the layer issues. And then there's something you can do anytime you have an angle that's greater than, I guess it depends on your frame of reference, but more than 45 degrees. So if you make this taper, if for some reason it doesn't need to be flat here, you just need this kind of hole here and that. If you can create the taper, you're going to get rid of a lot of support material because it can self-support. So 45 degrees is kind of that magic number where the material will support itself and you don't need any support material for it. So you can see it again because it's not switching back and forth between the support, because there's usually only one print head and it has to switch back and forth between the regular material and the support material and the regular material and support material. It's going to take less time, less material in general, because you're just doing this, you're getting rid of some there, and then getting rid of support material. This is also another case for FDM specific. These are all kind of make sense for both SLA and FDM. This one is FDM specific. Sometimes you think, oh, I'm going to core my piece art, I'm going to get rid of walls that I don't need, just because I think that'll go faster, right? Because your volume is less, in theory, right? If you were to look at these two solids as a solid, the volume in the cube is definitely much more than the volume of an I-beam of the same outside dimensions. That's not necessarily the case for FDM printing. Like I said, things are semi-hollow, and there's usually a minimum wall thickness. So as it's printing, as this area is hollowing out, it's going to actually add a couple walls around everything. So think of it more that surface area kind of matters more than volume of the part when it's talking about the amount of material used. So you can see this definitely printed a lot faster because it's doing hollow, and even though this has less total volume, it actually uses a little bit more material because it has to do all those walls. So just to sort of recap that last slide, for FDM, the part orientation in the printer matters a lot, so that's something to consider. This is not anything you'll have to do for this class, but just keep it in mind if you do it in the future. The layer-to-layer strength is not very strong, so also you'll have to consider that when printing. It's much stronger within the layer than against the layer. Overhang features greater than 45 require support. We kind of went over that. The holes, this is something also to note, holes are generally undersized, so if you make a hole a certain size, it's typically going to be a little bit smaller than you expect, and posts, so like external features, are going to be a little bit bigger. The round objects you saw, they kind of become oblong. You get much better resolution in the XY plane than in the Z-axis, so in your in your flat plane versus your vertical plane. Blocky parts can be faster and cheaper than cored out parts where you remove a bunch of material thinking that you're going to save on the volume. And then there should be very few instances. Of course, I told you our flute pieces are solid. There are some cases where you need things to be solid, but in most cases you can print them hollow or semi-hollow. This wasn't necessarily shown in that slide, but there are some similar things, or things that we should just recap. SLA printers will print solid, so it will do everything exactly as it is in CAD. So reduce material where you can, it'll speed it up and it'll make your part lighter. You saw the breakaway support material, where it makes these sort of scaffolds for your part. Again, we talked about how SLA printers will continue to cure over time. When they're exposed to UV light, they will start breaking down and become brittle. And then layer bonding is much, much better for SLA. So you typically, when SLA parts break, they typically don't break on the layer like you would see for an FDM part. Hopefully it clears things up, and hopefully you can explore a little bit with the parts that are in your kit.